if you had somebody pitching in baseball, so they're set and they're in that prep phase. So you're right here, acceleration is 0. Okay. Now, as I go and I'm going to pull back, effectively in my windup, I've got that acceleration that's negative. Now I stop myself and then I go to my force producing. So through here, and then after I release the ball, sorry, the hand's off screen, I'm going to have my follow through where I'm deaccelerating. So effectively what I'd have is a negative acceleration that has to go through 0 and become positive. And then from being positive, it's going to be negative again as I'm slowing that arm down. Now, and Josh, good work on your paper. Some folks have already turned theirs in. With the power clean, there's 2 movements to the pull. So your first movement to the pull is literally just getting the bar to your knees. And the ones that's at your knees, that's where you have the really powerful jump through. So you have a positive acceleration from the preparation phase. So it's a 0, and then it's going to be positive, and then it's going to be positive again. And then as we're getting into the catch position, we're going to go ahead and have another effective, it's going to go through 0 and then bring ourselves down. So we're going to have effectively a negative acceleration because we're pulling ourselves down under that barbell. So it's tricky. And the key is, that's why we start off first by looking at the degrees we're changing. So actually, let's do this. So let's say the arm starts here in some example I have. It then is going to cock back to here, and then we're going to be producing force until we get to say here. I have no idea what I'm drawing out, but I'm just doing it. And then it's going to then finish all the way over here. So effectively, this is 1, this is 2, this is 3, and this is 4. So the acceleration for the first part, because that's where we're starting, is at 0. Then when we cock back, we have to figure out how many degrees is this. So how many degrees does that change? We need to figure out the time it takes to go from 1 to 2. And if we have that information, okay, well, since we started at 0 and we had 0 velocity, the degrees that we covered and the time it took, degrees divided by the time, that's going to be our velocity. Now, the change in velocity is going to be that velocity we had from the beginning, from the beginning of the phase to the end. So the beginning velocity was 0, so that makes it real easy. And then we have the final velocity, which is going to be when we stop at 2 effectively. And then our average acceleration is going to be the period of time it took to go from one to the other. Does this make sense? So then when we're going to go from T to, oh my gosh, I need to start using the mouse with my left hand because this is embarrassingly bad. And then we're going to go to 3. Okay. Now we have our final velocity here. So that means we're going to have the velocity at 2, and then we're going to be subtracting that from the velocity at 3. And then dividing by that, and that is the time it took, and that's going to give us our acceleration for stage 3. And the same thing is going to happen again whenever we get to obviously looking at stage 4. So that's how you're going to figure out your degrees, which it's not perfect, but we're just trying to ballpark it. We're going to have the time it took, and if we've got the degrees we changed and the time it took, we can figure out our accelerations from there. And then that's where we're going to use the kinesiology examples and the tables I gave to you guys, where we're going to look at, okay, here's how many degrees here's the degrees we've changed, here's the length of the lever arm, here's the weight of the object we're moving, here's the weight of those segments of the body. Boom, now we can start figuring out the torque. And then, because we can estimate how far those muscles insert away from the joint, and now you've got your force that the muscles had to produce in order to get you those movements.
I have a question.
Yeah, go for it. What's up?
So, are we finding like the velocity for our joint or like in general?
You are going to find the velocity for just your joint as it goes through each of those phases. Don't worry about the in general.
Okay.
Yeah. And then, okay, let me. Okay. Yeah, Taylor, you can either do it in degrees or radians, because that's how we're going to be able to figure out effectively, because it's angular velocity, because we're rotating about these joints. And yeah, Gabby, the goal is you're just breaking it down for one joint. You're not breaking it down for the entirety. Now, here's the thing. The jerk is its own movement, just like the clean is its own movement. So I'm more than comfortable with you just doing the how the hips are going to work during the jerk. In fact, that's the thing that's really brutal about the Olympic or the clean, for example. If you think about it, you go prep where you're starting on the ground. Then you've got your effectively your windup is just dropping your hips to get started. Then you have your force producing, which is then broken down into two phases, the first and second pull. Then you have your follow through, which is actually getting yourself under the bar. Then you have getting into the catch, which is going to be another wind up because you're going down a little bit. And then you've got another force producing whenever you're standing up with it, and then a follow through all the way, at lockout. Real simple. Just, 8 different or 7 different movements to really worry about there.
Dr. Lane, when we're figuring out the force of the muscles that are operating in something, oh, well, sorry, I think that's a follow up to the current question.
No, go ahead. Go ahead.
Okay, then I know that in our examples in class, we've done something with the insertion angle. And I was wondering if there, like I've looked up the insertion points of muscles and been able to kind of estimate based on the picture, but I think I don't understand how to figure out what the insertion angle would be
Oh,
for the
see,
bicep force or
yeah.
whatever.
That's why that's not part of your guys' project, because that's gonna be a freaking nightmare.
Okay.
The reasoning for it, and that's why we're trying to just go with kind of average forces and average torques, is okay, let's take that bicep angle, for example. Let me go ahead and I think this will be hitting the right button. Okay, so if we're looking at the bicep angle, okay, so whenever my arm is straight, that bicep angle you can see is pulling in quite essentially an obtuse angle. But then as we come up, we can see how it's gonna be a bit more flat. And then when we get to the very top, we're in that tighter angle. So the angle changes the entire time. So if your movement was just the dumbbell curl, what we're gonna have is effectively through the force producing, which is all the way up, our angle is changing as we go through. And I don't want you to have to do the angle change every couple degrees. You're going to lose your damn mind. Instead, it's like, okay, what's the average force it had to produce if it inserts in this location? Now, for balanced equations, when we have somebody holding an object and just kind of holding it, we're looking at the forces produced. That's where I'm going to give you the angle, so you can go ahead and break that down.
So then, just to make sure I understand, we need to be finding torque, acceleration, angular velocity. Do we do force and resistance arms?
So that's why you're naturally going to have to you'll find the force in general, because you're going to have to do the balanced torque. So then all you do is just divide by what is going to be the lever arm.
I've got that then. Thank you.
And no worries. And Taylor, yes, you can do degrees per second. Radians per second is how you make the math work perfectly for everything we're doing. But I'm okay with obviously you guys at least understanding the concepts of using, okay, how far did this object rotate in this time period?
I've got another one.
Go for
I
it.
just won't monopolize if other people want to ask.
Hey, if everybody else has got the chance to use the chat, and they can unmute themselves too, so go for it.
Okay, so I'm thinking about the follow through. I know it's like a really specific question, but like the follow through in tennis for looking at the shoulder. So the arms over the shoulder, and so to me, it seems like, I mean, it's a complicated multiplanar movement, but it seems like the furthest area from the shoulder is the elbow, or pretty close to it. And so am I able to just for the resistance arm for each, then the forearm and the hand, is it just the length of the upper arm? And yeah.
No, it's okay. It's okay. So what you're doing is you're not far off. Remember, we want to look at the center of mass of those objects. And remember, it's the shortest distance along that lever arm to get it closer to the body. So, okay, so if I'm going to do like an awkward forehand from being like over my head. So if I'm here and I'm pushing, then pardon me, try not to swear too much. Okay, so if you guys kind of have the bird's eye view and I'm swinging across my body, okay? Now, as I'm going across my body, when I'm here, the center mass of my forearm is here. My hand is here and the racket would be wrapped around my head. So the racket is a real short lever arm. Make sense? So like the center of mass of my arm is here, okay? The center of mass of my forearm is probably about here, and the center of mass of my hand is here. So I wouldn't think of them as being perfectly at the elbow. They'd actually be shifted upwards a little bit. Now, if my arm was perfectly parallel to the position, which it's going to be maybe for a second, and hence why I don't expect perfection. I expect you guys to think it through. But then the center mass of the racket is going to be here, so it's going to be barely down the arm at all, so it's not giving me much resistance.
Okay, that makes sense. So it could be that the forearm has a shorter resistance arm than the shoulder does if it were bent like this, say. Okay, perfect. Thank you.
And so that's, as long as you guys are describing it and breaking things down in a way that's like, yeah, that makes logical sense, then you're good. But if you're going to tell me that somehow you're wrapping the racket behind your head and everything, it's like, I don't think that's how you're supposed to do things. So give me 1 second there, Josh. Okay. Looking for. Okay, so here is a great example of what a previous group did with their presentation from quite some time ago. Let's go ahead and go forward so you guys can't see that. Share screen. Okay, so this is for doing a knee sweep, but the first slide had their name, so I'm not trying to do that. So they have the key elements of the movement, which is what we're looking for, followed by they have their expert video. So let's go. Don't know if this will play it correctly, but we'll try it. Okay. All right, so give me a second, guys. New share. Switch over to the screen. So the key is, now we've got it in the share, so I can hit play. And you can see how the movement goes. Now, this is what's hilarious. They actually videoed each other. Sorry. It makes me laugh every time I see it. The funny thing is these ladies are best friends. Sorry, I can't help it. But here's where they did a great job. They used Giphy, I believe, .com to take so they can put the videos literally side by side so you can see the difference. And then each of them had their examples of how they were different from expert to the beginner. And you can see those differences in how the positions are going to move. So the same thing when we're looking at the elbow. You can see the difference in how the trunk's going to move. You can see how the hip's going to move. And then how the knee's going to move. And they even did the ankle. So does that make sense? It's kind of like what's probably going to be like, and that group got a perfect score on their presentation. So even though they didn't have the expert video from the side and overhead, I was being generous that day. That's absolutely fine. I mean, if one of you guys knows how to, I'm pretty sure Josh, you know how to do a clean very well, then, or clean and jerk, then you just use yours as a pretty, as it couldn't, not necessarily like super high level expert, but obviously someone who has ability there. And then you've got another individual who's got, you know, not as much skill. So we can definitely see a difference between effectively, you know, what the movement should look like, and then, you know, what somebody's trying looks like. And then you can break down those differences. Okay, so Taylor. Taylor, what is your movement? That could be what's going on. I just don't know what your movement is. Yes, yeah. So it'd probably be, think about it like a negative velocity and acceleration before you have that positive velocity and acceleration. Yes, and you definitely want to use references. Your book should be references, or should be referenced books, since we have two of them, and then whatever lit you've looked at to help you guys with breaking down the math. Because turns out with a lot of sports movement, there's already been a number of biomechanists that have done these things before. Why not look and see how they broke it down and make life a lot easier for yourself? Excuse me. Cite them in paper like you would normally. I'm not going to give you guys trouble for whatever citation style you use. You can use APA, Chicago, JAP, whatever works for you that you guys are comfortable with. Just use that citation style. Doesn't bother me any. Any other questions you guys want me to cover? You guys good? Anything else you guys really want to talk about? If you guys are good to go, guess we will go ahead and call it. Stay safe out there, guys. Keep finishing up those projects. And obviously, you know, yeah, papers are Thursday morning, what would be effectively before class. Presentations are due on Friday. And we've done all reviewing and everything else. So as far as I'm concerned, class on Thursday will probably be something like this again, where I just kind of hop on for a few. And if you have questions, I'll answer them. Otherwise, stay safe out there. Take care of yourselves. And I will see you guys back. You know, we'll review a little bit again next week as kind of brief little check-ins, and then you guys got your final. So anytime. Hey, you guys had good questions. It was fun, and hopefully that made things a little easier for you guys when you're still trying to work through your math, because it's the reason why I've been working the entire semester on this project, because it's really, really difficult. It's a lot of stuff you got to look at. And so, you know, take your time, really think about those muscle actions. That was something that a number of people struggle with in their homework, which is, when is a muscle contracting concentrically, eccentrically, and isometrically? That can be pretty difficult to see. So, and we can talk about that more next time. So
I do have a question about muscle action, if that's okay.
yeah, go for it.
Okay, so in I think that it might have been different in my homeworks because I've gotten to use eccentric muscle contraction, say dropping down into a squat
Mhm.
because it's gravity. But then so I'm looking at tennis, the shoulder. If you're pulling back in the windup,
Mhm.
that I think that that's that your like scapula is protracting and that your shoulder is horizontally sorry, abducting, and so it would be the muscles that are involved in that. Even though in it traditionally I've gotten to use that the adductors would be say eccentrically contracting.
Remember, it's going to be retracting because you're pulling back the shoulder blade as you're pulling your arm back, not
Yeah.
protracting the shoulder blade. That's okay. But you're right. Those muscles are going to be pulling you back. And then once we get back, the opposing muscle groups are what's going to be pulling us forward whenever we go and hit it. Now, what a lot of people mess up is they made the mistake with, which is, say, for example, they're doing a military press. They're like, yeah, I'm going to use my lats to pull myself down. Like, no, gravity's pulling you down. You don't need to like rip that weight into your own body. Instead, you're controlling it down with that deltoid, triceps, etc. And then the eccentrically, isometrically in the bottom, and then concentrically as you push it back up, and then isometrically at the top, and then eccentrically as you come back down. That type of muscle action is what kind of has been tripping some folks up. And the kind of same thing, they're like, yeah, when I squat, I'm going to pull myself in the bottom squat. Like, yeah, that's a drop squat. You can do that. That's typically not what people do, because if you were going and concentrically pulling on your hip flexors, you would lift your feet off the ground. And so you would literally land in the bottom of that squat, which is something that happens in Olympic lifting. They're pulling themselves under the bar. So just think about, is the muscle contracting? Okay. Now, if it's contracting, that means it's being used. So now is it contracting concentrically in that it's going to be shortening itself? Is it contracting isometrically, meaning it's not moving, or it's contracting eccentrically because it's going and being lengthened under load? That's the big thing that people are kind of, not a lot of people, but some folks are getting confused on it. And it happens. That's why, good question. We'll talk about it and maybe go into it a little bit more on Thursday. So enjoy the rest of your morning, guys. Nothing wrong with getting out early since we've gone through everything and we've gone through the review and everything else. So if you guys got questions, I'm more than happy to go through things. So stay safe out there, and I will see you guys on whenever. Mind you, there's only 8 of you here right now, so it's not like most people are here. So anyways, stay safe, guys. Talk to you more soon. Bye-bye.